In this video, we will learn how to perform linear regressions using a spreadsheet software. The program we will use is Microsoft Excel. However, the steps we will introduce here are generally applicable to other spreadsheet programs, such as Google Sheet, although there might be some slight differences. In this demonstration, we will analyze data from a research study investigating how the number of cigarettes smoked per week affects lung capacity. The dataset is provided with the video, and we encourage you to follow along by performing the linear regression on your own device as we walk through each step in the video. We will demonstrate two methods to perform linear regression. For the first method, we will first make a plot of the data and then add the linear trend line to extract the equation. For the second method, we will directly extract parameters of the linear equation without making plots. Let's start with the first method. Before making a plot, we should first identify the dependent and independent variables and decide which axis to place them on. In the research study investigating how the number of cigarettes smoked per week affects lung capacity, which of the following statements is correct about plotting the dataset? In this study, cigarette consumption is the independent variable and should be placed on the x-axis. On the other hand, the lung capacity is the dependent variable and should be placed on the y-axis. It is very important to determine our x and y axes before creating the plot. Excel is simply a tool, so it sees the data points as numbers without any meaning. It's up to us to tell Excel which variable goes where. By default, Excel assumes that the data in the left column are the x values and those in the right column are the y values. In this case, our dataset is already organized correctly. However, that might not always be true for other datasets, and you may need to adjust the order manually. To make the plot, we start by highlighting both columns of data. Make sure to leave out the column titles, only include the numerical values. Then click Insert and select the scatter plot icon. As you can see, the default plot in Excel uses the left column as X and the right column as Y, and does not show the axes titles. Therefore, it is important for us to label the axes so that we can keep track of the physical meaning of the dataset. To add axes titles, we can go to Add Chart Element, then select Axes Titles. This will bring up options for both the horizontal and vertical axes titles. Simply click both options to create text boxes on each axis. If you are preparing a plot for publication, you may also want to make more aesthetic adjustments to the plot. For the purpose of this video, we will not go over how to make such adjustments, but you can find how to do so in a separate video lesson. Now with our scatter plot, we can insert a trend line. Start by selecting the data points. Then go to the Add Chart Element menu, choose the trend line in the drop-down menu, and then select Linear. Congrats, we now see a linear trend line on our scatter plot. To extract the equation of the trend line, double-click the trend line. This should bring up a Format Trend Line side panel. Scroll to the bottom and check the boxes for Display Equation on Chart and Display R-squared values on chart. We should now be able to see both the y equals mx plus b equation and the r-squared value on the chart. Keep in mind that Excel, just being a calculator, does not know the correct number of digits to display for the equation. Sometimes it will show more or fewer digits than we want. To adjust this, click on the equation box to bring up the Format Trendline Label side panel. From there, we can adjust the format of the number. For example, if we want the equation to display 3 decimal places, we can choose the Number category and adjust the number of decimal places. Sometimes, when the slope or y-intercept are very small or very large values, you might want to use the scientific notation format instead. Another point to consider is the y-intercept. In the Format Trendline panel, we have the option to manually set the y-intercept. This feature is used when we are fitting data to a physical model that has a known fixed y-intercept. In our example of how cigarette consumption affects lung capacity, would it be appropriate to set the y-intercept to 0? In this example, the y-intercept represents the lung capacity when cigarette consumption is 0. Since lung capacity is not 0 for a non-smoker, it would not make sense to set the y-intercept to 0.
Now that we've gone over the first method, let's talk about the second method.
Sometimes, we might only want to determine the linear equation without making the scatter plot. In this case, there is a quicker way to get the equation parameters using a few simple Excel functions. Let's begin with calculating the slope. Select an empty cell next to the data, type equals slope, select the slope function. Then the software will prompt us to select our y values, then type a comma, and then select our x values. Then close the parentheses and press enter. This will directly return the slope value. Be careful when selecting values. We should leave out the column titles. The process to calculate both the y-intercept and r-squared value are the exact same as the slope, just with different functions. For the y-intercept, type equals intercept into a cell followed by selecting the y and x values. To find the r-squared value, use the function equals RSQ. We can choose either method introduced here to perform linear regression. Depending on the task at hand, if we need to generate a plot or to visualize the trend, then we will use the first method. If we simply need the slope, y-intercept, and r-squared values, then going with the second method will save us some time. Once we extracted the linear equation, we can use it to make predictions for unknown data. Using the formula y equals mx plus b, if we know the slope m and intercept b, we can calculate the y value for a given x. Alternatively, we can also determine any x value for a given y by rearranging the equation to x equals y minus b divided by m. In the previous case study, we found that lung capacity, L, is correlated with the number of cigarettes smoked per week according to this equation. Estimate the number of cigarettes a patient smokes per week if their lung capacity is measured to be at 4.2 liters. In this problem, we want to predict the number of cigarettes smoked, the independent variable x, using a measured lung capacity, the dependent variable y. To do this, we can first rearrange our equation y equals mx plus b to solve for x. We can subtract b from both sides, then divide both sides by m, giving x equals y minus b divided by m. Next, we can plug in our known values, shown here. This calculation gives x equals 18.9, which rounds up to 19 cigarettes. In an earlier example, we didn't include units in the equation, and the calculation still worked because the value used for lung capacity, 4.2 liters, had the same units as the dataset. However, a more precise and scientifically complete method is to include units in every term. The y-intercept b has units of liters, the slope m has units of liters per cigarette. So the calculation with units becomes the following, equaling to 19 cigarettes. Now, let's work through another practice example together. A group of researchers is studying the relationship between daily physiotherapy time in minutes and lung capacity improvement in liters for smokers. The data is provided below. Use a spreadsheet program to find the equation of the best fit line as well as its r-squared value. Using one of the two methods, the slope equals to 0.005,
The y-intercept equals to negative 0.025, and the r-squared value equals to 0.996.
In this relationship between daily physiotherapy time in minutes and lung capacity improvement in liters for smokers, does it make sense to force the y-intercept to be 0? The y-intercept represents the expected lung capacity improvement when the daily physiotherapy time is 0, that is, when the patient receives no physiotherapy. In this context,
It does make sense to set the y-intercept at 0.
because we would not expect any lung capacity improvement if a patient receives no treatment at all. Thus, forcing the line to pass through the origin is reasonable for this model. To set the y-intercept, we can check the Set Intercept option in the Format Trendline panel and enter the value 0.0. As you can see, once we set the y-intercept to 0, the y-intercept term disappears from the equation, and both the slope and r-squared value change slightly. As we mentioned earlier, whether we should set the y-intercept to a specific value depends on the context of the dataset and the physical model we are using. We should always ask ourselves whether forcing the intercept to that value makes sense scientifically, and whether it reflects our understanding of the real-world relationship being modeled. That's all for performing a linear regression. Thanks for watching.